Okay, my name is Stefanos. I'm a PhD student at Imperial College London, and I'm also a security researcher at ZK Security. I'm going to talk about vulnerabilities in snark implementations and in systems using snarks. This is a joint work with Jens, David Theodore, David Wong, Mohammed, and Benjamin Lifshitz. So, I will start by discussing what is the current state of ZKPs in production and also why we should care about ZKP vulnerabilities. Then I will briefly outline in which parts of the process when using snarks we can introduce bugs and what kind of bugs. And then I will briefly discuss what could be the impact of ZKP vulnerabilities and what are the threat models. And finally, I will present a taxonomy of ZKP vulnerabilities we did and also what kind of defenses are already have been implemented and what we can do next. So at the moment, we have various usages of ZK proofs. Some of them are on-chain, some of them are off-chain. The biggest one, I would say at the moment, is ZK rollups. But we also have Zcash, which has been pioneering that field for quite a while. And lately we have various, what I call them, ZK apps. And one example is ZK Login that will be presented right after my talk. And we have some private programmable L1s and L2s that heavily utilize ZKPs and some off-chain apps. And although we have all those different systems deployed and used by many users, there have been no single major exploit up until now. And although there haven't been any major exploit, there have been various critical vulnerabilities in systems in production. So there was a critical vulnerability in Zcash for quite a while, and someone from within Zcash identified it and fixed it. There was a vulnerability in Tornado Cash in production again. It was identified by some white hacker, and then it was patched. And there have been disclosures in systems that run in production, and there have been huge bug bounties given to white hackers again that identify the vulnerabilities. And finally, during audit reports, in many of those audit reports, there are like critical security findings. But still, no exploits. And there are two hypotheses. The first one is that there is no enough return of investment for attackers, but I don't think that's the case anymore because many of those systems handle a lot of value, so attackers could actually make a good profit. And the second argument is that ZKPs are complicated, and especially if you compare them with smart contracts, are more complicated, which I also don't think it's quite true now, especially with all the efforts of creating new classes and writing books and blog posts about ZKPs. So, for example, this is the underlying issue in one of the previous vulnerabilities, and it's pretty simple for anyone that has ever written circuit code to understand what's wrong here. And basically, due to that vulnerability, someone could have basically get everything out of Tornado Cash. So, at the moment, there has been some efforts. For example, there is the ZK bug tracker from 0xSpark that they have 25 vulnerabilities. But we wanted to further systemize the knowledge of what's going on in the space in terms of security. So, first of all, I will start with a very high-level overview of how we see the different layers involved when using snarks. So we start with a public relation, like we call it R here. It can be a program, it can be some specification, some logic we want to implement in a circuit. So the first step is to write the circuit, to handwritten the circuit. And that process can introduce many bugs, and we will see later that the majority of vulnerabilities are there. The next layer is the frontend. So basically, the frontend serves two main functionalities. The first is to compile the circuit to an intermediate representation. And that later can be our arithmetization, for example, R1CS. And the second process that the front-end performs is the witness generation. That takes some public input, some private input, the circuit, and produces our trace and our witness, which includes some private part, we call it W, and some public part, which we call it X. And then we have the backend that basically implements the three main functions of the snarks, which is the pre-processing, the proving, and the verification. And in both frontends and backends, there could be many bugs. And if we have a critical vulnerability, for example, in our snark verifier, that it's typically handwritten nowadays, but it can also automatically produced by our framework. Then it doesn't matter if our circuit is secure. Someone can exploit that vulnerability if our usage actually is impacted by that vulnerability. And finally, we have the integration layer, which is basically our application for on-chain applications. You can think of it like the smart contract that basically interacts with the verifier, or it could also be like some client-side code that interacts with the prover, etc. And lately, there has been a lot of work with ZK VMs, and the only thing that changes is that we give as input to the ZK VM a program, and then we have the ZK VM circuit, which is not, those circuits are not written by the end developers, but still there could be bugs there. So another way to see it is in a hierarchical manner. And here I have added two more layers, which is the hardware, the operating system, and the runtime, and the field arithmetic and elliptic curve libraries. And there could be bugs there. And if there are bugs there, our applications, our systems could be still exploited. But in this work, we don't focus on that. And what I want to show with that slide is that any bug on the lower layers can affect all the layers above. So if you have a bug in the front end, even if your circuits are correct and your application is correct, still your application can be exploited. Okay, so here are the basic properties that ZKPs provide. And for those properties, we use zero-knowledge proofs. First is knowledge soundness, then perfect completeness, and finally, zero knowledge. So we want all those properties to hold, and we don't want the bugs to affect these properties. And here are our three basic adversaries that we identified. The first one is the network adversary, which basically just can observe the system and the public values. The second one is an adversarial user that can submit inputs to a non-malicious prover that will then generate the proof. And finally, we have the adversarial prover, which has the ability to produce and manipulate proofs and submit them to the verifier. To better understand these three adversaries, here is basically a very high-level overview of a ZK rollup, where we have the user. The user submits some transactions to an L2 node that performs both the sequencing and the proving. And then the L2 node submits the proof to the on-chain verifier. So in our second thread model adversary, what it means, it's basically that only the user can be adversary and not the sequencer prover, but that's not our end goal. So when we do any analysis, we should consider the latest thread model where the prover can basically try to create a proof that will surpass the verifier. Okay, and what could be the impact of ZKP vulnerabilities? First, we can break soundness, which means that a prover can convince a verifier of a false statement. Secondly, we can break completeness, which means that either the prover cannot produce a proof for some valid inputs, or the verifier cannot verify the proof, a correct proof. And finally, breaking zero knowledge, which means that we have some information leakage about the private witness. So in our study, we selected 141 bugs, mainly from audit reports, vulnerability disclosures, and bug trackers. We only considered critical security vulnerabilities, and we did not consider any non-ZKP related vulnerabilities, such as reentrancy bugs in smart contracts. And here are our high-level results. So the majority of vulnerabilities are in the circuit layer, and the majority is also soundness bugs, which is the worst bug that can happen when we use ZKPs, because basically in the context of a ZK rollup, if there is such a bug and someone managed to exploit it, then all the funds could be drained from the ZK rollup. So why is the circuit layer the most tricky one, according to those results? Is what we identified is that there is a different programming model than the one that developers are used to. So basically, when you write a circuit, you have to think about both computation and constraints. And another way to think about it is computation is the work that will mainly performed by the prover, and constraints are the constraints that are going to be checked by the verifier. And beyond that, also when you write a circuit, typically you will have to do some tricks to optimize your circuit, to reduce the constraints, or basically to translate some logic from like your a program that you want to prove to a circuit, and that's pretty tricky. And sometimes both of them can be happening in the same part of the code. For example, here is a circum, and here we both define constraints, but we also perform the computation. But in other DSLs like Hello2, you have different parts of the code that one part of the code will do the computation and the other one will define the constraints. And there are three main types of vulnerabilities that can happen in the circuit layer. The first is under-constrained vulnerabilities, which means that we haven't fully add all the constraints to our circuit. So there could be some corner cases that we might have missed that can lead mainly to soundness bugs. Over-constrained vulnerabilities that are not that common, but mainly lead to completeness bugs. And there could be computational and hints errors, which is more on the computational side. Our constraints might also be buggy in that case, but it's more like how we're performing the witness generation. And we did the complete root cause analysis, and you can find more about all the different root causes in our paper. But here we have many examples for each of those root causes. But here I have basically highlight three different types. First, one root cause is that there is a different programming model, and that makes the life of the developers harder and more tricky. And for another issue here is that most ZK DSLs are too low level, so it's kind of tricky how to use them, and you have to be very professional to write proper circuits that are secure. The second one is that we identified that most circuits that have critical bugs actually implement some cryptographic primitives that are difficult to get right in circuits, but also developers try to perform aggressive optimizations that also introduced various vulnerabilities. And finally, there still could be common errors like API misuse, etc. And those are the main root causes we identified during our study. I have some examples, but I really suggest to look at the paper to see more examples. I want to highlight here that most of the fixes of the mitigations are kind of trivial. One very typical fix is to add a range check that you might have forgot, or to add some constraints that you forgot in the circuit. The next layer is the integration layer, and we identified 4 main vulnerabilities. I want to focus on the first one because it was the most popular one. Around 80% of vulnerabilities in that layer is passing unchecked data. And here, one example. And what happens here is that in circuits, mainly for optimization reasons, sometimes we have implicit assumptions that are not checked in the circuit, but we delegate that to the application layer to perform one check before calling the verifier, for example. And here it was a critical vulnerability that basically we didn't check a value we passed to the circuit that it's less than our snark field. And that could lead to other more severe issues in the application logic. The next layer is the front-end and back-end layer. In the front-end, there are very few vulnerabilities. We also believe the reason is because there have not been that many audits and people have not paid that much attention in the front-end. For example, if you start trying to implementing aggressive optimizations in your compiler, that might lead to severe vulnerabilities. And in the backend, the most common error is unsafe verifier. And verifiers can be either handwritten or automatically produced, and it's pretty common to have some issues there. Most of those issues have been detected through auditing, whereas for some other bugs, it's either through disclosures or the teams working on the protocols have identified them. Finally, I want to briefly discuss what is out there as a security tooling. So people have tried to use formal methods to identify mainly circuit vulnerabilities. So we have circumspect and ZK-app, which is basically static analyzers for circum. Then we have correct, which is a static analyzer that also uses SMT solvers to identify bugs in Hello2. And then we have a number of formal verification tools that mainly focus on identifying if there is under constraintness or proving that the circuits are not under constraint. And finally, we have some fuzzing tool, which is Snark Probe. And we had some mainly academic work on trying to find front-end compiler bugs. I would say that at the moment, only very few ZK DSLs have any security tooling. And also those tools have various issues from scalability issues, for example. It's a major concern in all the formal verification tools. Although there have been a good progress, I think there is a lot more space of experiment with formal methods to detect vulnerabilities in both ZK circuits, but also in the backend and in the frontend. For example, in the backend, there is some effort lately to verify the verifier, which could be interesting and could make using snarks much more secure. So finally, we also identified that there are some more theoretical attacks, vulnerabilities, and the main root cause is either there are errors in the original proof system descriptions, or there are some incomplete descriptions. So it's up to developer how will implement a specific snark, and the developer then might introduce some vulnerabilities. So, in conclusion, why do we have bugs in snarks? I would say that snarks, it's not just math. There could be implementation bugs that can break all the nice properties that snarks provide. And then here is a quote from Ron Rivest. He wrote that in around 90s for digital signatures, that users are being given enough rope with which to hang themselves, because basically they have to define some security parameters. And here I think the situation is even worse, because users are exposed to cryptography to the outer layers. So providing better abstractions, it's pretty critical to reduce the number of bugs we have in ZKPs. And also the complexity and the different threat model we have in ZKPs might lead to many vulnerabilities. And another issue we observed is that most protocols do not have specification especially applications that using snarks, they don't clearly define what they are trying to do in not even a formal way, even in an informal way. And I think if we had more specifications, it would be much easier to identify vulnerabilities earlier. And what we can do, we can create more learning resources to educate developers on how to properly write circuits. We can start writing more specifications and even develop tools to make it easier to write specifications for systems using snarks. And then we should implement, and there are already some DSLs that are more easy to use and more secure, because some bugs are not possible in those ZK DSLs by default. Some examples are Leo and Noir. And we can also develop better testing and security tools. As testing tools, I mean any framework that will enable developers to write tests to check for soundness issues, for completeness issues, up to like fully, formally verify our stack. So that's it. Our paper is going to present also in Usenix Security this year, in about a week, and here you can find our preprint. Thanks a lot.
Yeah. Great. We have time for one or two questions. If anybody has any questions. Yeah, Aline.
Hey, Stefanos, thanks for the talk. Really nice work, very useful for the community. You mentioned Halo 2 versus CirCom in terms of separating computation from verification. What did you find in your work? Did you find that one leads to less bugs than the other? And what would you recommend for a DSL to do? And maybe in general, you can speak to what a DSL should look like to minimize these types of errors.
I couldn't say that this is a main reason why we have bugs, that everything is like in a single function or in different functions. I would say what we identified about the ZK DSLs is that if the DSL is very low level, so there is basically no types, just working in a field, then bugs are way more easier to happen. Whereas if you have a type system and better abstractions for developers, then you can eliminate many classes of the vulnerabilities we have in our taxonomy.
Thank you. Thank you.
Yeah, it's a good question. Actually, I have a question. Oh, sorry, there's a question here. Please go ahead.
One thing, I don't know quite if this is what you meant by front end, maybe not, but many of the kind of classical mistakes that we get in crypto, like the cofactor things, are not being permitted even by very low-level libraries. But you would possibly change these things if you. So first of all, if you're going to try and deploy something really heavily optimized, you would maybe use different types of snarks together and all these other things. Or you might try clearing cofactors in the pairings. There's lots of other things that people will probably try and do once things stabilize, and that will be whole new things.
Yeah, so the question is like, if there are more optimizations in the front-end layer, then there will be more bugs. Yeah, and I think it's important to take basically some knowledge from other communities like C compilers and what they have done to identify optimization bugs, which is a major issue in C compilers and in SMT solvers, and try to define the oracles and develop techniques to detect such bugs in ZKP frontends.
Actually, so following up on that, do you think a way to reduce bugs is to try and use multiple proof systems at once? Or is that not going to help?
That could be an interesting case, but then you have some cost issues, right?
Of course.
You have to produce two proofs, so there is a trade-off.
Yeah.
But probably you could eliminate some of the bugs if you do that.
All right, very cool. Thank you very much.
Thanks.
Stefanos.